Alright, now we're going to go ahead and talk about electric fields. Now, electric field is a force like gravitational force. It is a field force. So let's talk a little bit about what it is.
Well, electric force can either be a pushing or a pulling force. Gravity is only pulling. Okay, it pulls things toward the earth. Electric fields, on the other hand, could be pushing or pulling. If it's positive, then it'll be a pushing force. If it's negative, it'll be a pulling force.
Okay. Now we have this here. It says an electric field is a region of space around a charged object in which a charged stationary object experiences an electric force because of its charge. So all in all, what does that really mean?
That means, like I said, that if it's a positive charge, there'll be a pushing force around it. Okay, we're going to represent that by lines in just a second. If it's a negative charge, it'll be a pulling force. And when you have a positive and a negative charge together and they're inside each other's electrical fields, then they'll pull each other closer together.
The lines for a positive charge point away from the charge, and the lines for a negative charge point towards the charge. Well, now, why is that?
Well, those are the lines that represent the electric field surrounding the charge. So a positive charge has lines going out away from the charge, representing its pushing force, and then the lines pointing towards the negative charge are pointing inward, representing the pulling force.
Alright, so just like how we have here on the picture, where it shows the negative has the lines pointing toward it, and the positive going away. And the last little bit we want to talk about here, we want to talk about the differences, and we will put two or more of these forces together. If we have a positive charge on one side, and we have a negative charge on the other, what happens with this?
Well, you'll have lines going out from the positive charge, representing its electric field. They'll go out from the positive charge in toward the negative charge, representing their attraction to each other. And the bigger the charge, the more arrows you're going to have, because the stronger and bigger the electric field is.
And do those, and you said that it goes towards the negative charge. Does the negative charge have arrows as well?
Yeah, it has arrows pointing inward. They kind of overlap whenever you have a positive and negative charge together. But yeah, the negative charge has its own arrows going in toward it. So if you have two charges, you'll have double the arrows that you would if you had just one charge.
And they'd be going the same direction because it's positive and a negative, correct?
Yes.
Now, what happens if I have more arrows for my positive than I do with my negative?
That means that the positive charge is much stronger than the negative charge. If you had twice as many arrows for the positive charge than you did for the negative charge, that would mean the positive charge is twice as strong.
Now suppose we want to make a big static electrical charge. Well, we could use something like this. This is called a Van de Graaff generator. It's named after Robert Van de Graaff. So here's what happens. Electrical charges are deposited on this rubber belt. The rubber belt turns and redeposits the electrical charges up here on this metal ball. Now, since this next part of the demonstration rocks, I'm going to put on my rocker wig of science. Yeah! Now, start the rubber belt turning. Electrical charges are being deposited on the metal ball. They're running through my arm and being deposited in me. And look, it's building up in my rocker wig of science. See, since these charges are all the same, they're not attracting. No, they're repelling. They're pushing apart. So they're pushing the hairs of my rocker wig apart.
How's it going, everybody? Today we're going to talk about Coulomb's law and what exactly it means to us in physics. So can you tell me what Coulomb's law is?
Well, a long time ago, there was a guy named Coulomb who he theorized that the amount of force that two charges exerted on each other was inversely proportional to how far they were apart. So if you increase the distance between two charges, they will experience less force from each other. The amount of force will go down. That's an inverse proportion.
So when you say force, is that a vector?
It is a vector. It depends on the direction, and it depends on the distance between the two objects.
Okay, so how does that affect us? What does that mean if they're positive or negative?
Well, if you have a positive charge and a negative charge, then the force will be going from the positive charge to the negative charge. That's the direction. The forces move from the positive charge to the negative charge.
Okay, so I'll do Q1 is the charge of object 1. And then Q2 is going to be the charge of object 2. Q2, ditto more charge of object 2. Okay, and then K. Well, let's talk about K for a second. We know that we had, for our constant last time, it was the gravitational constant, which was the 6 point, right?
Yeah, something like that.
Is it going to be the same number?
It's not going to be the same number. This is the electrostatic constant, which is 9 times 10 to the 9th Newton meter squared, the meter part squared, over Coulomb squared. It's just a constant kind of amount of force per Coulomb you're talking about.
Okay, and then D is going to remain our distance, correct? Nothing's going to change with that?
Right. It's still the distance between the two objects.
Okay. And then FE, that's going to be our electrostatic force.
Joel in the end is taking his shoes off. He now has no insulator.
Oh my god!
Save none.
Take a look at an example problem. It says two identical conducting spheres are placed at their centers of 0.3 meters apart. Well, 0.3 meters, that's going to be our distance. So this is going to be distance. We know distance because it's going to be meters. One is given a charge of a positive 12 times 10 to the 9th Coulomb. So that's going to be another.
Yeah, that's the charge of our first object, and it is a positive charge.
That's Q1. And the other is given a negative charge of 18 times 10 to the negative 9. Negative 18 times 10 to the negative 9 Coulomb. That's going to be our Q2. So we already have our distance, Q1, Q2. Well, our K is going to remain the same, which is the 9 times 10 to the negative 9.
Yep, that will never, ever, ever change.
And the first question is to find the electric force exerted on one sphere by the other. So I'll go ahead and get a blank sheet here, and we'll go and take a look at this. Welcome back, ladies and gentlemen. Now we have this problem set up for us. We have all this information. We're trying to look for electric force or electrostatic force. We have our distance, our Q1, Q2, and we know that our K, never changing, is already listed for us. Now we need to plug it into our equation. This equation, you might have seen something similar to this when we did the gravity equation, where it was force of gravity equals to G m1 m2 divided by d squared. This is force of electricity or electrostatic force is it K Q1 Q2 divided by d squared. So essentially we're going to do the exact same thing we did back in gravity in this module here. So let's go ahead and plug in our information. We don't know what FE is, so we're going to keep FE by itself. We know that K is going to be 9 times 10 to the 9th. We know that our Q1, which we're going to multiply that, multiply all these together, is going to be a positive 12 times 10 to the 9th. Now you can do it either way. You can do it through the e's, or you can do it with the times 10s. Whatever is going to be best for y'all. And then there's going to be our Q2, which is a negative 18 times 10 to the negative 9. So negative 18 times 10 to the negative 9. All of this is divided by our distance squared. We said our distance was 0.3 squared. Now I would put this exactly into the calculator just like this, where I do the top part first, and when I do the top part, I divide it by my distance squared. So that's what I'm going to do now. I'm going to take that 9 times 10 to the 9th, open parentheses, 9 times 10 to the 9th, close parentheses, multiply by open parentheses, 12 times 10 to the 9th, close parentheses, and multiply that once more by a negative, don't forget that negative, 18 times 10 to the negative 9. But to get that, hit enter and then divide that number by my distance squared. So 0.3 squared. And that is going to leave me with an electrostatic force, Fe, of a negative 2.16 times 10 to the 13th power. Times 10 to, 13. So that's going to be the answer for this equation. Now, this is a negative number. When we take a look over here, a negative number just means that it's going to be an attractive force, while a positive number is going to be a repulsive force. So negative is going to pull things toward it. Repulsive is going to, positive is going to push things away from it. But there's one other thing that we want to go into, and that's going to be is after equilibrium has occurred. So after equilibrium has occurred, well, what this means is essentially if we were to take and connect both of these charges together, put a rod that extends between both of them and touch them, they're going to equal each other out. So how we would do this is we would just average them out. We take the average of both of them. So I'm going to go ahead and make some room for myself over here. We know what this is, so I'm going to go ahead and erase this. We want to average these out. So if I take positive 12 times 10 to the 9th and a negative 18 times 10 to the 9th, I add them together and divide by 2 for the average, then then they're both going to be Q1, and that's going to be, what is it, Q1, it's in after equilibrium, that's the word I was looking for, equilibrium. So Q1, I'm going to put an E next to it, just to show you that's in equilibrium. It's going to be, what is it, negative 3 times 10 to the negative 9. Well, if both of them are going to be in equilibrium, we still need two charges to do this equation. So my Q2 E is going to be negative 3 times 10 to the negative 9. So both of these are going to be the same. Now, the rest of the equation doesn't change. Just these two here. And it's important to remember that if they're in equilibrium, you don't just put it one time, you have to put it twice. Because if not, there's going to be no electrostatic force between the two of them. It's just going to be, one just being there. So K is equal to 9 times 10 to the 9th. And then our Fe is what we're looking for. And on our distance, it's still going to be 0.3. So we'll plug this into our equation. We said Fe is what we're looking for. Is going to equal to K, which is 9 times 10 to the 9th. Multiply that by our Q1, which is negative 3 times 10 to the negative 9. And then our Q2 is also negative 3 times 10 to the negative 9. All of this divided by my distance squared. So when I plug this into the equation, I'll take open parentheses 9 times 10 to the 9th, close parentheses, multiply it by negative 3 times 10 to the negative 9, close parentheses, and multiply that by, again, negative 3 times 10 to the negative 9. Close parentheses, and then divide that number by my distance squared, so 0.3 squared, and that's going to get me an electrostatic force of 9 times 10 to the negative 7. Alright guys, that should be it. If you guys have any questions, please raise your hand and talk to your teacher, call them over, and we'll be happy to answer whatever you guys have for us. See you next time. See y'all later.